some object, we all know this, if I let something go, this ball right here, then an external force will act on it. How do I know? Because the ball has an initial velocity of 0, and clearly it does not maintain the initial velocity of 0. It begins to move downward, so it has a downward pointing acceleration. And in fact, this acceleration was measured by Galileo and people after him, and it has the interesting property that it is uniform for all objects. So any object in the vicinity of Earth accelerates down, the acceleration is called the acceleration of gravity, and in our fancy units, it's about 9.8 meters per second squared. This is my son's 10-kilo shot put ball, and when I hold this, I'm preventing it from falling down with the standard acceleration of gravity by applying a force directed upwards to the ball. Newton's third law then tells us that if I'm applying a force to the ball, directed upwards, then the ball is clearly applying a force to my hand, directed down, and believe me, I can feel it. Of course, gravity is going to play an important role in what goes on. It's also a force that acts all around us, so let's quantify what we said. The weight of an object is defined to be the force gravity applies to it. We know that objects on Earth fall with an acceleration that I told you, 9.82 meters per second squared. So the force of gravity on any object is directed always down. It's given by the mass of the object times this constant, which is why we confuse mass with weight, but separate the two. M is a property of the object. G is a property of Earth. We often say that I weigh 59 kilos. A more correct statement is that my mass is 59 kilos. My weight here on Earth is mg, which is 59 kilos times 9.82 meter per second squared, or, doing the calculation, I believe I did it right, 579 kilos times meter per second squared, which is 579 newtons. My weight is 579 newtons. We'll play more with the specifics of Newton's laws, but the first thing we need is to understand some very deep and important consequences that are mathematically derived, and Newton derived them, from Newton's laws. And the most important of these take the form of things called conservation laws. There are quantities that you can define for a physical system that do not change. So let's look at this. And the first conservation law involves this quantity called momentum. We define another vector called momentum. It's essentially the velocity vector, but multiplied by mass. So roughly it measures the amount of oomph, the amount of inertia, some people say, that the object has. A refrigerator moving at 2 meters per second has more momentum than a tennis ball moving at 2 meters per second. The reason this is important is because F, being satisfying Newton's law, let me rewrite it again here, Newton's second law, F is mass times the rate of change of velocity. Since mass does not change, it's a property of the object, F could be thought of as the rate of change of this momentum thingy. And so if F is the rate of change of momentum, we have something very deep. Imagine that there are only two objects in the universe, but there are forces between them. So A acts on B, and the velocity of B changes, and B acts on A, and the velocity of A changes. What we know, though, is that the force that A applies to B, whatever it is equal in magnitude and opposite in direction to the force that B applies to A, which means the rate of change of A's momentum is equal in magnitude and opposite in direction to the rate of change of B's momentum, with the consequence that the rate of change of the total momentum, add up these two vector objects, the total momentum cannot change. Now add more objects, and the same principle extends. There is in the universe a total conserved object, the total momentum of the universe, and that cannot change. Moreover, if you get to isolate some subset of the universe so that it doesn't interact, there are no external forces on it, then the momentum of that little group of objects is completely conserved. All that forces can do is allow objects to exchange some momentum. Some momentum can be transferred from one object to the other, so the momenta of the two objects change, but the total is unchanged, and we say that momentum is conserved. We call this a conservation law, and such conservation laws are critically important. Let's take a look at what this looks like. This is a toy, appropriately enough, called Newton's cradle. It has a a row of 5 steel balls hanging from a framework, and we will pull one ball off to our left so that when I release it, it will impact the row of balls with a horizontal momentum pointing to the right, and let's see what happens. What happens is that the incoming ball comes to a complete halt, transferring all of its horizontal momentum to the next ball down the line, which transfers it to the next and so on until the last one leaves the pile with essentially the same momentum as the one with which the initial ball came in. We can repeat the same process with 2 balls and see a similar interesting process. We can do 3, and if we are ambitious, even 4 balls, and reproduce the same results. I hope I convinced you that we can see mathematically where Newton's laws lead to momentum conservation very directly. A little more math that we're not going to follow through shows that there's another way to find a conserved quantity that is associated deeply with circular motion. So it involves picking a center for motion. And it's called angular momentum because circles are parameterized by angles. And it's a quantity that is given, it's related to momentum. Here's our friend momentum. But it's the momentum times the radius of a circle in which one moves. And what one finds is if you have a collection of objects that are all moving together, you sum up, just as with momentum, the total angular momentum, the mass of each of them times the velocity of each of them times the radius at which each of them is moving around the circle. This is assuming everybody's moving in a circle. There are more complicated expressions in other cases. Then this angular momentum is also conserved in that it can be traded between different parts of a system, but the total is conserved. This is going to be extremely important to us because things in space tend to spin, so let's demonstrate that with our valiant demonstrator. Standing on a platform and holding out some weights, I have my friend Derek start me spinning slowly, and what we see is that as I pull the weights in, they have a significant factor of m, and I'm making their r smaller. My angular momentum is conserved by making all of me spin faster, and I can control my speed. When I pull my arms out, I slow down. When I pull them in, I speed up again. This is a great demonstration of the conservation of angular momentum, if not perhaps of exceptional physical grace. There's another conservation law that you can show follows from Newton's equations. Imagine an object upon which the only force that acts is gravity, like this rubber ball when I throw it up and down. So as long as the ball is in the air, essentially gravity is the only force acting. And what we know is that when I throw it, as it moves up, it'll slow down, and then as it comes down, it'll accelerate, moving down. This is formalized in the following statement. It turns out that if you form the combination m times g times h, where m times g is the force that gravity applies, and h is the height of the object above something, my hand, the thrower, it doesn't really matter what, we'll show why. And if you take this quantity, which we call gravitational potential energy, and add to it this combination of speed and mass, m times v squared over 2, this combination is called the object's kinetic energy, then the sum of both of these is constant. As h increases, the object slows down, because that's how gravity works. And as it falls down, it speeds up. And this mathematically expresses this. Notice that it's clear from here why I could have measured the height from the floor or my hand or the bottom floor of the building. It doesn't matter. That just adds a constant that never changes. So adding a constant to the energy until very late in this class will be completely irrelevant. Now, this is very nice, but it's only true if the only force acting is gravity, and in general there are other forces that act. And so in general, this conservation of energy is violated. But not really. What really goes on is that whenever there is another force other than gravity acting, a typical example is friction. If I roll my chair back, it slows down. It had kinetic energy, and the energy disappeared. Where did the energy go to? Well, if you listened closely, you could have heard that some of it turned into sound energy. It's also true that there is friction in the bearings of the wheels, and that converts some of the energy to heat. Heat is a form of energy, and friction is a force that converts kinetic energy very happily into heat. So there are many different forms of energy: sound, light, heat, chemical energy, electric energy, nuclear energy. We will talk about all of them in turn. They'll all show up. when you add them all up together, it turns out, in any process, the total energy in the universe is conserved. And again, if you isolate a chunk of the universe from the rest, then the total energy in that chunk is conserved. Energy is neither produced nor destroyed. This might come as a surprise to all the politicians who talk about the need to produce energy or conserve energy. Both of those are political terms, but scientifically, energy can neither be produced nor destroyed, and it can be conserved. In fact, it always is. It's a very important concept to us. Let's remember the units in which we measure energy. So they follow from this equation. Energy is measured in units of kilogram times meter squared per second squared. If you plug it in, you'll see that both of these terms have the same units, which is good because otherwise adding them up would make no sense. And this is dignified by the name joule and indicated by a J. So this is joule. And it's hard to have exactly a sense for how much a joule is. So let me help you by perhaps suggesting the following idea. Our body, to push this chair back and forth, to move my arms, I'm producing kinetic energy by converting chemical energy from the food I ate. And we measure the energy content of food in calories. We all have some sense of what a calorie is. So 1 joule is about 4.2 calories. Fun demo of conservation of energy is this bowling ball pendulum. I'm holding it up against my face. It's got potential energy because the angle elevates it from the floor. I release it. It acquires potential energy, swinging it to the other side, converting it back to potential. And when it comes back, if energy is conserved, it will not go any higher than it did before, and therefore will not smash my face. Let's try it. This is it. Those are Newton's laws. I don't know if you appreciate what I mean by this is it, but by the end of this class, I think you'll have a deep understanding of this. In a very real sense, this is all of science. Certainly all of physical science. The equation that governs science is F equals ma. The rest of certainly a century of physics is figuring out the details in the sense of figuring out M, what kind of objects are in the universe, what do forces act on, and figuring out F, what are the forces between various objects. One way I want you to think about this equation, fancy name is a differential equation, but what this really means is it's a prescription for figuring out what the universe will do next at any given moment. And the way it works is this. If we know the forces that act on things, and we happen to know at some instant where all of the relevant objects in our system are, and because this only determines the acceleration, we need to know how they're moving, because if a ball is here, clearly there are several different motions it can do under the influence of gravity. It could just fall, or if it is initially moving up, it'll go up and then go down. But once you know where it is to begin with and which way it's moving, then gravity takes over and tells you the rest. In other words, you can take the positions and velocities at a given instant, use those to figure out what the forces are. Perhaps where it is might influence what forces act. Is it touching my hand? Is it not touching my hand? That allows you to figure out the accelerations. Those tell you in turn how the velocities will change, so you can figure out the velocities an instant later. Using those velocities, you can now figure out the new positions, figure out the new forces, and repeat. This process is called solving a differential equation. And in essence, what the universe does is it solves Newton's equation all the time. What this allows you to do is, if you have some knowledge of what we call the initial data, all of the positions and velocities of the parts of your system at any given instant, you can predict what everything is going to do into the infinite future, and also you can roll the clock backwards and figure out where everything was at any given time all the way into the indefinite past. And as I said, most of a century of physics goes into filling in the details of F and M and applying Newton's laws in various situations and finding the consequences. Let's start that process with the force that's most important to us, which is gravity, in the next clip.